Okay, the question is given by this. So we have a function f that is just log of x1 plus log of x2. The x has two components. The domain omega is some subset of the strict first quadrant. So the question is asked is given as follows: is the maximization of f subject to the constraint that x belongs to this omega. The first question is, suppose x is the optimal solution, then it is possible that x star is an interior point. Second question is, what point satisfies the second order necessary condition? So because for the first question, if you want to show whether x star is interior point or not, we just think if x star is an interior point, then the first order necessary condition will be gradient equals to 0. The gradient of f for this function, the gradient of f is just that. And x1, x2 belongs to the first quadrant, belongs to omega, which is contained in the first quadrant. That means this has to be a non-zero vector, right? Because both components are positive. So in this case, the x star cannot be interior point, because at the interior point, if x star is a local minima, then it's also an interior point, the gradient of f at x star must be 0. But we have shown that gradient of f at any point is not 0. Okay, so this violates the first order necessary condition. It cannot be an interior point. So if we ever reach a optimal point, then it must be a point on the boundary. So the second question is if any point satisfies the second order necessary condition. So for maximization problem, the second order necessary condition is to check the Hessian and see if the Hessian is positive, negative definite, or for any if it's on the boundary point, then we need to check if for any feasible direction d, the d transpose Hessian d is a negative number. Okay, so the Hessian of this function f is this. So it is a negative definite matrix, since both of these two components are negative. So this means that no matter what d you multiply, d has to be a negative number, and that means for every point, the second order necessary condition is satisfied.